Okay, so I'll start off. My name is Ephrance, Eunice Namugenyi, and the next page will introduce me in depth. Our paper is entitled Enabling Robust Sensor Network Design with Data Processing and Optimization, Making Use of Local Beehive Image and Video Files. So with me, I'm the first author and I'm the presenter of this paper. I've written this paper with David Tugume, Kigwana Augustine, Benjamin Rukundo, all from the Department of Computer Networks at the College of Computing and Information Science, Makerere University, Uganda, under the Ademnea project. So about me, I am a PhD student in software engineering in my third year, and I'm a lecturer at Chambogo University at the School of Engineering Design, Department of Electrical and Electronics Engineering. I guess that's it about me. And then I'll give you a background about our paper. First of all, when we're talking about sensor networks, we have a bit of challenge when it comes to transmitting large data files, especially across remote, hard-to-reach environments. And there is that complexity of work when it comes to handling sensor data, especially the huge files like the videos and the images, which becomes more difficult because of the existing technologies such as the GSM and Wi-Fi, which we actually use in this paper. What we add is the edge computing that helps with the data optimization. And of course, it helps in mitigating these challenges when it comes to transmission of huge data files over hard to reach areas. And we are using a specific application of Beehive management. So like already mentioned, the problem statement is that sensor networks in specifically beekeeping have issues when it comes to transmitting large data files in environments that are challenging. So there is a need to optimize data before it is transferred over the cloud for our specific application of Beehive management. So this particular paper has, of course, both the technical contributions and the research contributions. Under the technical contributions, we propose a compression technique that handles Beehive photos and videos, and it the technique kind of outperforms the existing good algorithms in terms of compression ratio when it comes to settings with limited resources. Then there's development of an aggregation algorithm for simpler data as an addition. In our case, we have temperature and humidity. Then on the side of the research contributions, there is a thorough evaluation of different compression methods. Of course, without the best, which is BZIP2, and then comparison with both the Wi-Fi and then the GSM network. And then we have notable gains when it comes to transmission time, especially in low bandwidth situations. So at the end of the day, at least we will be able to see the performance of Wi-Fi when it comes to transmission time. So this is our architecture design. You can see on the edge, we use the Raspberry Pi as our microcontroller. And then here we have our sensors placed on the microcontroller, and then this placed at inside the beehives to help us get the data, whatever is happening in the hive, using the videos and then the images. And then we use our two modules, the Wi-Fi and then the GSM. And then in between there, we have these algorithms, the compression and aggregation techniques, or in brackets, edge computing, happening on the data before it's actually taken over the cloud. Then on the other hand, we have the application user or the user application, where, for example, the the bee farmer is able to see what is happening in the hive. They don't have to keep moving to the hive to monitor what's happening at the hive. So with this architecture, they are able to actually use our suggested parameters to check what is happening in the hive. So our major parameters, of course, throughput comes in because we have to make sure that data moves from one end to the other. Then, of course, I mentioned the data compression. Then we have retransmission of data in a way, because we ensure that all the bits of data, that bytes of data that we have sent actually appears at the extreme end. That is what I mean by data retransmission. And then, of course, the time aspect comes in to pull off the latency. Packet loss in a way, because we make sure that the data retransmission, that packets which are not sent are actually resent on the other side. So about the Wi-Fi and how it functions, it uses the IEEE 802.11 standard. And of course, Wi-Fi is known for providing high-speed data transmission over short, medium distances. Characterized by high data throughput and low latency, which of course we will see at the end of it all. Then GSM, we use the GSM SIM 800L EVB. And of course, GSM provides coverage even in hard to reach areas, reliable communication, low power consumption comes in by the choice of devices that you choose. And then of course, the price, relatively inexpensive. I talked about the video compression algorithm that we proposed and how does it function. Here we have a sequence of original video frames encoded into the format that we want them, and then compression happens, and then we have the bit stream stored and then transmitted on the other side. Then of course decoding happens to take the messages back into their original format. Of course, even reconstruction in a way to take them back into the original video sequence, and then we have the transmission happening. This is a lossy compression format, and of course we expect some picture quality to some extent to be lost as compression is happening. Then when it comes to the image compression algorithm that is proposed, this one works by removing information that is not easily visible, like even for the video compression to the human eye, but of course keeping the information that is needed for a person to see exactly what is happening in the hive without necessarily losing the real fact of what is happening at the hive. Okay, so of course we have that fact that image quality is sacrificed to achieve small file sizes. To a certain extent, there is that degree of compression, and of course we monitor the loss of quality, which can be adjusted, yeah, and then saving these images in JPEG format. So when it comes to evaluation of these algorithms, whose designs I have shared above, we have compared this proposed algorithm with the BZIP2, which is one of the best compression algorithms that has been written in a couple of papers. And then our proposed algorithm, in terms of compression ratio, is clear that it performs way better, of course, at the expense of the quality. So in this row, we have the length of videos, and then you can see the original sizes in bytes. And then this is BZIP2, which is a common compression algorithm, reducing the original file size. As you can see, when you go down the row, there is a reduction. But then our proposed video algorithm, this is our final size, there is further reduction, and we can see this from the compression ratio. You can see the BZIP compression ratio at 1.52, and then there's that increase in compression ratio, which works for us because now we are proving the performance of this algorithm by the compression ratio. So this is what is happening for video compression. And then when it comes to image compression, you can see, okay, this is the camera and the pixel setting. We said we can compromise a bit of the quality to a certain extent that the farmer or the viewer at the moment can still see what is happening in the hive without necessarily losing, the bits that they want to actually view in the hive at the moment. And then we have the original bytes. You can see the 10 megabits here, and then we can see the bzip2 final size. After this is image compression, you can see there is a reduction. And then in our proposed image algorithm, you can see there's a further reduction. And of course, the performance again still comes in. The performance is not as good as you could view for the video compression, but there is still that improvement in the compression ratio. So this is a graph to show you the compression ratio versus the file size. And you can see that for these our proposed compression algorithm, there is a compression percentage of over 75%, of the files from the original size of bytes. There is over 75% reduction in file size. Then I talked about the aggregation algorithm for simple numeric data, for example, when it comes to measuring temperature and humidity. And how does it work? How does this work? Of course, the first step is data collection. But this, the focus of this algorithm is to make sure that we can get the data into many rows, but then have a single file. All these rows of data are stored in a single file. So in a way, we minimize on the time that the data takes to move from input to output. So we have the CSV file management, where the algorithm checks if a CSV file exists, and then new data is appended to it. This is what I was talking about, where we have data appendment, like you have rows added into that single file, and then we have the same file taken over to the other side. And we will see the performance of this. Of course, then we keep monitoring the file size, and then we have data transmission. We want to make sure that our factors are kept constant, or we keep improving them in a way, as we shall see in the results. Yeah, so we are here, we have the number of rows in CSV keeping on increasing down. And then of course, as you append more files, you have the bytes increasing. But the beauty about this is the average time. These are times taken at 3 instances, and then the average time is taken of how much time is taken for the files to be transported from one side of the network to the extreme end. You can see that the time is almost the same, no matter the increase of the number of rows. It's only when we reach 100,000 rows, of us in the CSV file, that the time actually jumps to 4 seconds. But you can see that the time frame is almost the same. So in a way, we are minimizing resources. We are keeping our transmission time in check, And so this graph, you can see this graph is the average time taken to send these rows of files to the server. You can see the number of rows in CSV, and then you can see that the time is actually the average time taken to send these files is the same until we actually jump to 100,000. That's when we jump to 4 seconds, which is good if you're talking about minimizing resources. And of course, this is still the same graph, though it's the average time taken to send the number of bytes of data. Of course, as the rows increase, even the bytes of data sent over the network increase, but you can see the consistency in the time aspect. So how do we conclude on this paper? We have realized that our proposed compression algorithms performs much better than the well-known BZIP2. You can see that the BZIP2 achieved a compression ratio of 4 for a 24 MB uncompressed image, while our algorithm achieved a compression ratio of 10. So from 4 to 10, I mean, 10 is higher than 4. And then even when it comes to the video compression, the BZIP2 achieved compression ratio of 2.5 for 135 MBs. And then our proposed algorithm achieved a compression ratio of 22.5 for the same video. So the higher the compression ratio, the better the compression algorithm. So this is just an example to show you a test. We have a file size of 24 megabits. After using the BZIP2 algorithm, you can see the file drops to 6 megabits, and then using our proposed algorithm, it now reduces further to 2.3 megabits. Yeah, so we can actually prove that our compression algorithm performs way much better. Of course, BZIP2 in a good way excels in data preservation, but like I mentioned, when it comes to like a bee keeping, we don't really need to keep the accuracy of the video. Yeah, we at the moment there's a certain stage where you can compromise on the video quality and then increase on the compression ratio, because I mean we are looking at small networks with small payload sizes. Okay, so we have that acceptable data loss in media files that justifies the use of lossy compression. Okay, so our proposed algorithm, in conclusion, succeeds in reducing the file size, which is good for us when it comes to network measurements in terms of the factor of compression ratio that we have put up. Yeah, so I talked about the aggregation algorithm, which also in a way optimizes the network transmissions. You know, it helps in reduction of the time. The time is kept constant, like we saw. And then, of course, this in a way reduces the use of the channel, reduces the overhead, reduces the energy, you know, that you have to put in, and then also reduces the risks of having extra packet collisions. Yeah, so I want us to compare, like I mentioned a few. Of course, here I just put Wi-Fi, but I mean, at the end, when I'm trying to conclude, we try to compare the performance of our network, both using Wi-Fi and then GSM. So in this first row, we have, okay, this is just the video algorithm and the final size of the bytes, like we have already been seeing. And then we have the average sending time when we are using Wi-Fi. You can see the time. And then we have the average bytes sent per second when we're using Wi-Fi. And then, of course, on the other hand, we have GSM. And we have concluded on the functionality of this, which is the same for both cases, but using Wi-Fi specifically. So looking at transmission time, I said, like, I'm making conclusions using Wi-Fi, but the case is quite similar for GSM. When we look at the BZIP2 compression, the transmission time decreased by, you can see, for the first file, by 53.85% from this calculation. From that calculation, and then file 2 by 39.10%. Okay, from this calculation. Of course, when you're looking at the time decrease, you get the original minus the final, and then over the original times 100, and then you have your percentage. When we look at our proposed algorithm, you can see that the percentages have increased. Yeah, for Wi-Fi, we have 75.30% for the first file, and then we have 94.48% for the second file, which proves our proposed compression algorithm actually performs better for both Wi-Fi and GSM, though I used Wi-Fi to conclude. Yeah, so in conclusion, our suggested compression algorithm performs exceptionally well, both in GSM and Wi-Fi, and this is critical for practical use. We don't want to really kick out GSM and Wi-Fi because they have their advantages, which I mentioned at the start of the presentation. This paper as a whole has presented a holistic management perspective on optimization of data transmission of large files, specifically using Beehive images and videos to prove the performance of these in sensor networks. Of course, emphasizing the importance of how edge computing can come in. We've used the algorithms, the compression algorithms that are performed on the data before it's actually sent over the network. Yeah, so thank you very much. Thank you for your attention. I welcome